Okay, hello everybody to this week's ISGC seminar. Today's speaker is Jackson Levi, and he did his PhD at the University of Malta, where he graduated in 2014, and now is he since 2022 an associate professor at the University of Malta, and he's also at the Institute of Space and Astronomy there, and he's at the same time the chair of the Cosmoverse. I guess it's a project. I think you will tell us more about it. And with that, I hand over to you. The stage is yours. Thank you very much for giving this talk.
So thank you very much. Hello, everybody. Good. Well, for me, it's afternoon, but good morning, good evening, or good day, wherever you are. Yes. So today, I'm going to talk a little bit about something which we do in. I mean, this is a theory community mainly, or maybe only. And something related with model building. Now, model building, how do we do this? We do this, whatever flavor of gravity or cosmology or scalar tensor theory or wherever we find ourselves. We normally take some information, sort of processed information, either from observations or maybe more fundamental from symmetries in these different theories and this sort of stuff. And using that information, we try to build models in the main, right? That's where we want to get at. So what I want to show you here today is something, yes, there's machine learning in the title, and it's about using machine learning to look at new physics. But the whole point of this is a new sort of suite of different techniques, which, yes, they rely on machine learning, but it's about really at its core, it's about model building. So it's not only that, but that's what I want to show you mainly here today. So there's that side of things, and yes, about Cosmoverse, it's this logo in the middle. So if you know what this is, great. If you don't, I'm going to say a little bit at the end about this. But this, just in short, is basically a big network which is based in Europe, but which has a global reach. And we organize things like conferences, workshops, but also a lot of online stuff, seminars like this, teaching tutorials. And also we're working on a big white paper. We want to bring the whole community together around this white paper. So I'll say how you can contribute to that a bit later on, but at the end. So in this talk, what I'm going to do is I'm going to talk a little bit about the motivation for looking at this at new physics, but this may be preaching to the choir in a certain sense. So a lot of that may be stuff that we know already. From there, I'm going to take a toy model example, not a toy model, but an example of one kind of this new physics. So in particular, teleparallel gravity. This is a very nice way of applying these new machine learning techniques because it's algebraic and the numerics are not super complicated. So we can try these new techniques. And then finally, I'll show how this compares with traditional techniques and these new techniques. Okay, so sorry. Okay, so as we know, our standard concordance model, our standard model of cosmology is based mainly on curvature connected with general relativity. So we've had over now 100 years of this. We have over the last just over 20 years now a cosmological constant on top of this, and we know we have matter from the standard model of particle physics. And just to nuance this language a little bit, we have to change this. We know this already. We have to change this to get our concordance model, both with new physics, or not new physics, but with concordance physics from the early universe and with concordance physics from the late universe. So to try and nuance this language a bit of early and late or local. So in the early universe, we know for many decades now, or for a number of decades, that we need inflation, cosmic inflation, and we accept this. Okay. But even within the concordance model, if we look at the early universe, there are many statistical questions regarding data and how this model agrees with that data. For some decades, we've had the lithium problem. So if we think about the production of Big Bang nucleosynthesis of the primordial species in the universe, we've had this for a few decades now, and it's grown in statistical attention. Also now, there's some anomalies related with the production of helium, just fairly recently. Also, recently, if we look at CMB, Planck CMB, there are some hints of a closed universe, which would be counter to everything we've been doing in theory cosmology for a very long time, I would say. There's not so many works beyond a flat background cosmology. Staying with CMB, there are, again, I say mild statistical tension, like 2 to 3 sigma. So if we look at the CMB, we see many small scale anisotropies, but there's a lack of large scale anisotropies, which may not be a problem, but it is a curiosity, let's say. There's also some issues, for instance, with the cosmological principle, looking at cosmic dipoles in the CMB. This now, again, these are not very serious problems individually, but they do start to add up. And just to mention the last two, the fact that we get non-zero birefringence in the CMB at a certain statistical level brings us already to ask questions about the early universe. And the last one, just on this, so we know we need dark matter in galaxies, and we know we have dark matter from CMB, but there is, again, small hints at the discordance in the amounts that we get from CMB dark matter and small scale dark matter. So we have these 2 to 3 sigma problems in the early universe. What about the late universe? Late universe is the problems came up much earlier on because they're much more direct in our faces. We have the classic numerical problems of dark matter, called dark matter, the embodied simulation problems in a sense of missing small satellites, the density distribution within galaxies, classic problems with dark energy, having a fundamental explanation of what on earth is cosmological constant and whether it's dynamical in general as a realization of dark energy. More recently, there's also been the suggestion of the cosmological best fit parameters on the sky maybe having some direction dependence, again going back to this cosmological principle idea. And also with the Tully-Fisher relationship, which tells us how in particular with the baryonic Tully-Fisher relationship, which tells us how baryonic matter moves inside galaxies, whether this may have some redshift dependence. So both in the early universe and in the late or the direct measurement side of the universe, we have these sort of 2 to 3 sigma problems. And most recently now, probably you've heard of it, but maybe not, this idea of cosmic tensions, or in particular at its core, H0 tension. So H0 tension, to mention here again, since we're a theory community, we should be very much aware and motivated by this problem, because it is, number one, in many studies, this is at 5 sigma already. And secondly, it really goes to the core of developing new models of cosmology. So if we look on the right, if we're looking at direct measurements, and there are many direct measurements of the value of the expansion of the universe at current times, H0, this gives us a very high value of H0, which is something in the 74 kilometers per second per megaparsec. Over here, I just give 2 examples, the famous SHOES team or the SHOES project, which is mainly looking at type 1a supernovae with different calibrators. In this case, they're using Sheffield variables as calibrators. Another big example is this old Holy-Cow collaboration, where they look at, there's a method of cosmography. So looking at arrival times from strong lensing events in the direct measurements, basically. On the left, on the other side, we have CMB. So both Planck and dark energy survey are both related with CMB beta. The difference between these 2 things is that in the late universe, we can make direct measurements of H0, whereas in the early universe, we need to put in some cosmological model. Obviously, in this case, we're using flat FLRW with lambda CDM, so the concordance model. And again, we get a very different value of H0 over here. Again, so this should motivate us when we're developing models to try and resolve this problem. And in fact, so a review we had a few years ago from something called Cosmology Intertwined, which maybe you've seen, but most probably very famous now, which sort of enumerates all of the let's say the most robust analyses at the time related with this problem. And I guess the biggest thing to take away from over here is that there are so many of these studies that it gets very hard to even read the text. It becomes pixelated. On top, we're seeing mainly early universe measurements. So mostly the CMB stuff that I was talking about. And at the bottom, we're seeing these direct measurements. And you can see that the bottom part sort of aligns with that orange vertical band, which is the shoes measurement. So they're very consistent with that. And at the top, mainly, they agree with the Planck measurement, which is, which again, that gives us a low value of H0. Also, you may say, maybe there's just a problem in the way we look at the CMB. On the top also, there's some measurements related with no CMB, with just Big Bang nuclear synthesis combined with BAO. So this is very important to say that this is something that is not so much related with a particular phenomenon, but with early versus this local measurement. And something else to mention as well, again, we're a theory community here, so just to mention, not just background, which is where we find H0, but also on the perturbative sector. So in particular, when we're thinking about scalar perturbations, if we're looking at the clumping of matter, there's a much milder tension, but still one that appears to be of interest to the community and growing in nature, which is the S8 tension. S8 has got to do with the density parameter of matter, so that's a background level omega matter, but also this sigma 8, you can see in this expression, which has got to do with the fluctuations of matter at the scale of 8 megaparsecs. Again, just looking at this whisker plot over here from that review that I mentioned, we get, okay, the top early direct measurements coming from the CMB, obviously they agree with CMB, but at the bottom we start to get different values. So something to think about. And also very much here, I don't know if you can see my cursor, but very much here on the right, over the summer, there was this result from the DAISY collaboration related with a number of things, but one of the things that was mentioned was this W0 WA plot, where lambda CDM would, in this parameter space with W0 equal to -1 and WA equal to 0. And you can see that these posteriors, those colored region plots, are beyond 2 sigma away from that. So there's already some, in this regime of looking at new physics, some hints at dynamical dark energy, let's say. Anyway. Okay, so as I said, I think I'm preaching to the choir. However, so this tells us we need possibly new physics, or maybe there's something wrong in the way we make measurements. But let's say that we need new physics. So new physics, what guide do we have? One guide we have from quite a few decades ago now is Lovelock theorem, which tells us if we want to demand that we keep second order equations of motion, what assumptions do we need to break to make that a reality? Or another maybe more modern way of looking at this is through this graph here, where we can see different kinds of classes of different theories of gravity. So we can add invariants like f of r gravity or f of whatever you want, whatever flavor you like. Gauss-Bonnet, anything like that. You can look at quantum theories of gravity. Very popular, we can add new fields like Mondesky, which I'll say a bit about later on, scalar tensor theories. You can change dimensions, which now seems to become less popular in the literature. More exotic approaches like entropic gravity and some of these other things. And something that I would take it as an example is changing the geometry, the underlying geometry. That's why I mentioned it a few times. So in my case, I'm going to look at teleparallel gravity, but what I show here can be applied to any different class of theories of gravity. So the thing I would say to take away from this is not so much what I said just now, but that this, while it looks like a finite space of models, is in reality, as we know, an infinite space of models. So we need extra information to try and square the circle, to try and connect this infinite space of different possible models with getting what's our job in theory, to try and come up with different theories that explain what we're seeing in observations. So we need somehow either to intuitively guess the correct class of models and then refine the particular expression of that class of models with the data. Or alternatively, we need some method. And this is what we see in the literature. We see different ways, different approaches of taking our information about the real physical universe and inserting that into these different classes to reconstruct in a certain sense, or find symmetries that give us different cosmological models that resonate better with reality. So as I said, I'm going to take the example of teleparallel gravity. So I'm just going to give just a few slides on the motivation for that, but then we'll see how we can models in this class of theories using traditional methods, Markov chain Monte Carlo in particular, and then how we can turn that on its head and try and have the so-called different classes of models, and I focus on the word classes, as the result. So our result will be that f of r, or in this case, f of t, or also at the end, we'll see a scalar tensor theory, so that the result in the end is the potential, for instance, of a scalar field. But to go a little bit on the very deep history, not to focus too much on this, but just to mention some of the background of teleparallel gravity, because sometimes it feels like this is a new theory, but it has its roots in decades-old theory related with Poincare gauge gravity. And the idea here is to borrow from particle physics the idea of gauge theory, basically, to try and turn global symmetries to local ones, and by breaking that, to try and produce fields in the end, to try and connect that to a gravitational theory. And this background, you know, from starting from the 50s onwards, you know, gives us in the end this idea of Poincare gauge gravity. And what I would say, as in a nutshell, the most important part of this would be that curvature and torsion result as field strengths in that theory. In particular, where torsion is, number one, non-dynamical in classic Poincare gauge gravity, and that it turns out to be the field strength of the translation group. So it has some roots in this gauge theory approach. There's a nice review down here from the 90s that goes over all of these details. Anyway, from that time onwards, there were a lot of concerted efforts to try and use this non-dynamical torsion, to try and do something practical. In particular, it became very popular to look at quantum theories of gravity. And the idea in that case was that torsion may be connected with these different quantum theories, and maybe curvature is in the classical regime. But there's a lot of different expressions or ways that this was put together. And as we know, we have thousands of curvature-based different modified theories of gravity. So the sort of the sales pitch of teleparallel gravity is that looking at these f of r, Gondesky, and so on, many theories or many modified theories of gravity, which really came about not just in the late 90s, but even before that, to also consider torsional theories of gravity. Why? Because we can get unique theories of gravity that don't, you know, some of these are analogs of curvature modifications, like f of r. You can write f of r as a torsional theory of gravity. All you're doing is changing the algebra. But there are also other theories that are not just algebraic, that they actually really are modifications. And we'll see one of these in a few slides. So just to be concrete, practical in this, what we're doing is we're changing the geometry. And what does geometry mean for us? Geometry means the connection. So if we think about what gives us curvature and generativity, it's a Levi-Civita connection, which then builds up to the Riemann tensor, as we know very well. And we have this nice famous quote by Wheeler, connecting matter, space-time, and then curvature. So what we want to do is want to map that Levi-Civita connection with the teleparallel connection. So instead of having a parallel transport that gives us the Riemann tensor, we want a so-called closing of the parallelogram, in this case, which gives us a torsion tensor. So we're changing the second part of Wheeler's famous quote, where instead of matter tells space-time how to curve, it's matter tells space-time how to contort or how to become deformed. So we don't get biased towards curvature. And not to throw a lot of equations into the mix, just to give some mechanics behind this. So in teleparallel gravity, we can write something called the teleparallel equivalent of generativity, and the key word there being equivalent. So in the classical regime, this action at the bottom, whatever it is identical to generativity. So we can't tell to experiment which geometry is better in the classical regime. So we call this TEGR. This is based on that torsion tensor that I was that I was mentioning before, and there's some of the details of that. The fact that instead of a metric, we depend on what's called the tetrad and the spin connection. But these are not so important for this talk here. It's just that these things exist, is all I want to say. And as I was saying before, one thing to mention is that we have this nice review, or I hope people feel that it's a nice review, that was published last year, related to the whole spectrum of different teleparallel theories and how it connects from fundamental physics to cosmology and observation analysis. Not to go through all the different flavors mentioned here, and there are more. I just want to show that there are many different ways of modifying this TEGR, very similar to the different ways of modifying GR. In particular, one very interesting way of doing this, and this particular flavor of teleparallel gravity, so it's called F of T, it's the same logic as F of R. So we're taking, instead of having this T as our TEGR action, we're adding an unknown function, F of T, which we have to choose in some way, which is my point about model building. We have to choose in some way. So F of T is like the extension part of this. So if F of T is a constant, it basically is the cosmological constant. So I'm taking this on as a toy model, and I'm taking it on as a toy model because there are some questions about some of the foundations related to this, but just for the purpose of today, for me, this is very nice because if you see the Friedman equations at the bottom, in particular, the first Friedman equation, so in black, we have our what we get from GR, and then in red, we have the F of T extension. And most importantly, to notice over there that F subscript T means F of T derivative T. So that means that we have a very, very simple modification of the Friedman equations, which is really what we want when we're doing numerics. We don't want extremely complex theories that may be intractable, or maybe even if they are tractable, they may take so long to solve that we can't really say something meaningful about them because they may have too many degrees of freedom and so on. Anyway. So in cosmology, we care not just at background, but also on the perturbative sector in F of T. So if we take the scalar vector tensor perturbations, the tensor perturbations which are related with gravitational waves are by and large, very similar to GR. So we get the same polarizations, same speed of propagation. We don't get so much in difference. But here, like in the slide, we can see that if we look at the scalar perturbations, and we can go through all the mechanics, but one way to see what modification we get out of this is through the effective Newtonian constant. Effective Newtonian constant, it does change, as you can see again in red at the bottom. You can see we have Newton's constant, but we have 1 plus F subscript T. So that derivative is actually very important for us because it tells us how our choice of F really affects the clumping of matter. It also affects, obviously, the expansion profile of the universe because it appears also at background. There's a lot to come from this. And just to mention one other flavor of teleparallel gravity, so you don't say, I just showed one, since we are the theory base over here. Something else which we proposed a few years ago in relation to Hondesky gravity. Hondesky gravity, probably most people here will have heard of this, but if not, so this is the most general second order theory that involves only one scalar field. Since it's the most general theory that gives us second order field equations of motion for one scalar field, obviously this turns out to be, it will turn out to be quite complicated, as you can see by this L2, L3, L4, and L5 Lagrangian terms at the bottom. And on the right here, we have a picture by Hondesky himself, who actually left the field after he put this theory together to become a painter. So this may be a cautionary tale for us in that sense. Anyway, one limitation of this is that with the fairly recent measurements of gravitational waves, we know, and I'll show this in a slide in a minute or two, that gravitational waves move very close to the speed of light. In terms of how fast they propagate. The problem there is that it kills off a lot of the more exotic and in particular the most studied parts of the model space that this framework gives us. So that was our motivation. And in this work here, we started to talk in the box at the bottom, and we started to think, how can a teleparallel analog, not the equivalent, an analog of Hondesky gravity we put together. And in the end, we found that this gives us an infinite space. Teleparallel gravity seems to be generically lower order in nature. So we had to put some extra limitations beyond the second order field equation requirement. We had to put, these are physical, like bound, the fact that we don't have parity violating terms. But something else we have to put in is that we're quadratic in torsion. I mentioned those torsion tensors, that we don't have like an infinite series of summations, which would still give you a second order set of field equations. Anyway, putting all that aside, the details are not so important about the way that this looks in the end. But in the end, we do get the same terms we get in standard Hondesky, curvature Hondesky. And we get, I don't know if you can see my cursor, but we get this G-teller function, which is actually a very simple function. It's just a function of many scalar invariants. In practice, it becomes very complicated because there are a lot of scalar invariants. And these are mainly related with the scalar field phi, so phi and its kinetic term. There's also this T-ax and T-vec, which are purely gravitational, and these are a decomposition of the torsion scalar. And then there are these new terms as well, I2 and these IJs. And these don't appear as well in standard Hondesky gravity. These are couplings between the derivatives of the scalar field and that torsion tensor. In standard Riemannian geometry, these are impossible, because if you do that with the Riemann tensor, you will get higher than second order theory equations of motion. So that's why these are novel in that sense. Anyway, so our interest was not so much the scalar perturbations, but to look at the tensor perturbations to understand if you take tensor perturbations, in the end, you should get some gravitational wave propagation equation like this thing in the middle, where you get 2 of the 4 alpha parameterizations that tell you how your theory behaves at perturbative level. So alpha m would be related to the amplitude of gravitational waves, but more importantly, alpha t would be related to the excess speed beyond the speed of light that your waves would be moving at. So we want our alpha t to be 0, right? Why? Because of the measurement, just to show one slide, because of the measurement related with the LIGO-Virgo cluster and this gravitational wave that they detected, and its accompanying electromagnetic counterpart detected by the Fermi telescope. And again, you can see the constraints down here at the bottom, where we have the speed of gravitational waves moving up to 1 pi in 10 to the 15 at the speed of light. And in fact, you can really see this in this expression of alpha t here, under the first point. So in black, we have the standard Hondesky expressions, and you can see that this involves derivatives of G4 and G5. And whatever, if you think about it, whatever combination of G4 and G5 functions you put into this, there's no combination, there's no magic combination that's going to give you 0. And this is why people expected that gravitational waves would move at a different speed. Because they expected Hondesky, the most exotic parts of Hondesky, to be correct. So this big swath of the model space of Hondesky gravity was eliminated. So what we get with this expression of teleparallel Hondesky are these 2 terms in red over there. And one nice thing that we get out of this, just to end on this in terms of the foundational theory, is that this revives, in a certain sense, that infinite models, or part of the infinite model space that Hondesky gives us. Because we can choose G-tellers that counterbalance these terms and give us an alpha t, which is 0. So just to advertise this a little bit. Okay, so I said that this is about new ways of creating models, of building models, which is what we are doing, right, in the theory sector of cosmology. Let's see the standard way of probing different models. And in particular, I'm going to cherry pick f of t. So I'm going to take, what we're going to take, as in physics, we always take a power law model. Let's take a power law model, okay, PLM, for our f of t, which is an extension of GR, or TEGR. And the thing to see is that the controlling parameter in this power law model is going to be the B1. Why? Because the amplitude alpha 1 depends on that and the other cosmological parameters. So B1 is the thing that we care about. And here, okay, these constraints are not so strong, but just to show something, Before I had mentioned the G effective over here on the y-axis, I have G effective over Gn minus 1. That means that if I get lambda CDM, I'd be looking at that red dashed line at 0. So that would be lambda CDM. And if you see, so here I show two kinds of data sets. So in blue, I'm showing cosmic chronometers, which, if you don't know, has got to do with the differential aging of galaxies. And there is a number of data points related with that. There's the type 1a supernovae, SN, which is the thing that we always hear about, and in particular related with the shoes theme. And that HR is a prior we put on these data sets related with the shoes estimate of H0, or one of the shoes estimates of H0. And this also we put this so-called KVNO data set. This is related with quasar data, and it's related with possible variations in the fine structure constant, which we don't get variations in the fine structure constant. So we're putting constraints on these parameters here. And as you can see in both cases, whether I include this KVNO or not, I'm always consistent with that 0, even if only marginally, we're consistent with that 0 point. But more traditional as a method, let's look at what's called the Markov chain Monte Carlo approach. So here we're trying to fit, in particular in this case, we're trying to fit very simply the Friedman equation in this case. We're looking at a whole bunch of different data set combinations, and we're seeing how that fits my model. So there's a lot of information here, but in particular, just to say a bit, so on the left-hand side, we're looking at CC and SN together with either on their own in blue or in green, red, and purple. We have what we call priors on top of that. So there's some estimates of H0 or trial values on top of that. So there's the R19, which is one of the shoes estimates of H0, but there's also HW, which is holy cow, which is the strong lensing measurement I mentioned before. There's also TRGB here. TRGB is one of the few local measurements that gives a relatively lower value of H0. And this value that we use here actually comes from the Chicago group, which now seems to be changing in value, but that's another story. On the right-hand side, we also include BAO data. And maybe one thing to highlight over here, if you see the bottom left corner of this BAO case, you can see how B1 sort of calibrates, there's an anti-correlation there, sort of calibrates the value of H0. So I can get different H0s by changing this value of B1. And that also has an effect on omega matter as well in this. Again, the point of this is not so much to fit different models, but just to show, so you can see like the whole, what we want to get out when we're doing these analyses. We want to get out all those parameters that I was mentioning, so the Hubble constant, omega matter, and that new parameter B1 for these different data sets. Over here, I guess one thing to notice is that H0 doesn't really make it all the way up to the mid-70s that we were talking about when we're talking about H0 tension. But it does get somewhat closer than lambda CDM. And these AIC and BICs, these have got to do with statistically how well the model behaves. So it's competitive with lambda CDM, but improvements are possible, let's say it that way, as a punchline. We can, since we were talking about perturbations before, we can also have a look at what happens at the perturbative level. So on top of the things that I had before, in this analysis, we changed slightly that SN case, type 1a supernova. Here we're using Pantheon Plus, the latest sample of supernovae data sets from the shoes and Pantheon teams. And on top of that, we put this RSD, redshift distortion space data. That has got to do with the spatial distribution of galaxies in space, obviously. So this is telling us about, at perturbative level, how matter is distributed. So in addition to the parameters I mentioned before, we also get a fit of sigma 8 over here, which is got to do again with the fluctuations of matter on the scale of 8 megaparsecs. And here we get much better H0, more, basically all the values are much more consistent. And even if I look at this through the prism of S8, as I was mentioning S8 earlier, if I look at this through the prism of S8, in turquoise or blue, I don't know what color to call it, we have the S8 parameter coming from the legacy Planck collaboration, the last data release. And in purple over there, we have another value, which is like the local value coming from the kids collaboration. And in green, you can see again that that's Pantheon Plus and RSD data set that I was highlighting earlier. And you can see, okay, there's some uncertainties, but it's consistent with both of these. So this model, whether you like it or not, it has some promising features, let's say. But again, what are we doing here? And what's the problem here? So the problem is that I picked a class of models of modified theories of gravity, which then gave me a modified cosmology theory. And then after that, I chose again an ad hoc model, and I looked how well this behaved. Now, this is not realistic. I can't go through every functional form that under the sky that I can think of, and every other different class of models that is possible. So I would say the main theme of this talk is, can we use this new suite or these many different methods of machine learning to reconstruct, to try and get the data and go backwards? As theorists, we want to develop models. So can we go backwards, take the data and make the models? And again, this is something we're already doing. We're doing it by choosing functional models of the scale factor and then reconstructing our Lagrangians. We're doing this by looking for particular symmetries in actions. We're doing this in many different varied ways already. The difference here is that we're using modern techniques. That's what I would say is the main difference. And here I'm going to show two methods. I want to try and stick to the time as much as possible, but I'm not sure. So I want to show two methods, which are one is very popular in the literature, called Gaussian processes. And I mentioned some studies here and also some of the pros and cons. And then I want to mention something called neural networks, which is less popular in the model building literature, let's call it that, but which has some promising tools and some promising directions in its future. So to start with Gaussian processes, so Gaussian processes is something, it's one kind of machine learning technique, which actually goes back a long way in terms of trying to interpolate data, trying to remove noise from data. So this has actually been applied for a number of decades now in other fields. And the basic premise here is that if we take those data points that I was mentioning earlier, and we assume each one of them is not so much a data point, but at the peak of some Gaussian, hence Gaussian processes, we can try to find the relationships between these different distributions. And that's the whole point of Gaussian processes. So we want to define something called a kernel. This kernel will have some parameters. These parameters will not be physical. They will purely be related with how these different points are connected together. So to give an example, this is Gaussian processes. Let's take a Gaussian kernel. This is one of the most popular. Over here, x and x prime would be my data point. So it would be two redshifts, for instance. And on top of that, if you look at this, you'll see that there's a sigma f and an LF. So LF tells me how far away these data points can be for them to be somewhat related together. And sigma f tells me what the amplitude or the power of that correlation, the strength of that correlation should be. So that's why I say these are not related with physical things. They're not related with the value of the Hubble constant or that sort of stuff. They're related with really how these data points are related together. And if we use this method, we can get a Hubble diagram, as I was, inferring earlier. So we can get a Hubble parameter versus redshift. Again, it's the same sorts of data sets, so cosmic chronometers, supernovae, BAO. That's the pure data sets on the left. On the right, we put this Schuh's prior on top of that. Again, over here, we can get a variety of H-naughts. The thing to notice with these estimates of H-naughts, besides there being a spectrum, I think the other thing to notice is in general how small the error bars are. That's one thing to notice. And the other thing you can really see this low uncertainty, even in the two graphs, that at low z towards 0, we have very low uncertainties. Anyway, so I can get it, as I was saying, I can get these estimates of H0. Here I'm also showing this D function, a distance function of these estimates of H0 from the priors I was mentioning before, the Schuh's, TRGB, and Holy Cow. But that's not the main point of this. So the main point of what we're talking about today really is about model building. So, okay, so we can use Gaussian processes to reconstruct the Hubble diagram. So now, in a sense, I have a Hubble diagram that doesn't depend on my physics in a certain sense. It depends on, okay, astrophysics, the measurements that give us the Hubble parameter, the expansion parameter. But I've put in no lambda CDM. So let's consider that f of t class of models again. So if I'm doing numerics, I need boundary conditions. In particular, if we, going back to what I was saying at the very beginning, lambda CDM in the late universe is not so bad. There are issues, but it's not so bad. Mainly people try to modify gravity in the early universe. So if we take lambda CDM in the late universe, meaning f of t is equal to lambda at roughly z0, that gives us a boundary condition. And again, to remember, what is f of t? F of t is an extension in the red here beyond TEGR. So I'm extending my generativity in that sense. Not to go through all the details of the numerics, but again, in that box there, we can see how we have our GR Friedmann equation, and in the red, how we have the f of t extension to that. Using basic numerics of changing that f subscript t derivative into a so-called propagation equation. So that means at different z's, how does a z redshift depend on a previous redshift in terms of this f of t? So I can put in what's called the central differencing method. It's not so important. And I can propagate my boundary conditions forward. And this is the point of why I chose f of t. Whether you like this or you have problems with this, it doesn't matter so much. But since f of t is second order in nature, it makes this process much simpler. And importantly, it means the uncertainties give me something competitive. And it really does work. So if I apply this Gaussian processes method to the data, and then I use these numerics, I can plot an f of t versus t. And this is what we want, right? We want to have, we want in the end to have a functional form of our general class of theories, whether it's f of t in this case, or a potential if I'm looking at scalar tensor theories or whatever. So here what I'm looking at is really f of t versus t which grows with redshift as we go to higher numbers. And again, it's the same data sets we had before. On the right, again, to emphasize that here we have a trial value or prior, which comes from the shoes theme. But in both cases, you can see that horizontal dashed line. So that would be lambda CDM. That's when f of t is a constant, in particular when it's equal to my lambda or minus 2 lambda in the action. Anyway, and you can see here that as I go to higher redshifts, so as I go to higher torsion scalars, I start to move away from lambda CDM. The indication is mild, to say everything, but we start to see something non-trivial here. So it's interesting. And this could be applied to many other places. And it has been applied in some other places, but not as widely as I would have expected. Since it's powerful in that case. And maybe before going to the other slide, just to mention, we can, obviously we can put in functional forms and we can try and see where we have turning points and try and let that inform what functional forms to take. So if we're looking for extra information, intuition, this is one place to find that. We can find that motivation. But we don't get nothing for nothing, unfortunately. So GP has some problems. In particular, it's got the overfitting issue that I was mentioning earlier. So there's an indication that maybe the uncertainties are a little bit unrealistic at z very close to 0, so the value of h0 with its uncertainties. And also I mentioned the Gaussian or square exponential kernel. There are other kernels, and there is a bit of a question on the consistency of different kernels. By and large, they do give the same values as each other. But there is a question, which kernel to choose? So there are these two, let's say, cons on top of this. So what can we do? So in the literature, there's a whole bunch of papers on GP, but not so many on neural networks in relation to model building. So one thing we wanted to do, and we have now a few papers on this, is to use what's called neural networks. In particular, in this example, I want to show artificial neural networks. The word neural tells us that this somehow is a connection with the brain. And if you've used ChatGPT or heard of it, then you definitely have probably looked it up and had a look at the diagram that looks most probably very much like this, where each of these circles is a so-called neuron. So it accepts a signal coming in, it sends a signal out, depending on certain features. These are organized into layers, and the neurons between these layers would be connected together like with these arrows. But these, by and large, would be the hidden layers. Then I have an input layer, which could be my redshift, for instance, for different data points. And out of this, I have Hubble parameter. In this example, I have Hubble parameter and the uncertainty with that, with the different Hubble parameter data points. So what I do in this is I send my data through this whole network. And what I want to do is the same thing we did with GP. I want to reconstruct my Hubble diagram. Now, it's not on its own. We need to set it up, obviously. So what does that mean? It means, for instance, choosing the number of neurons, the number of layers. How can we choose this? If we take the best optimized ANN or artificial neural network, we can define something called a risk function, which is the difference between my observed data and the uncertainties with that, and my predicted from the ANN, my predicted values for those corresponding redshifts. And I want to obviously minimize this risk as much as possible. So I need to find the minimum point. Also, each of these neurons and the arrows as well, all of these things have, again, more hyperparameters. So not physical parameters, but parameters related with the way these signals are handled, whether they change or whether something happens to them, that sort of stuff. And not to get into the details of what the neural network is doing, the basic point is that we want to so-called train our neural network. So that means we pass our data through it a number of times until we're at the best, most possible case where the neural network is really reproducing, as I was saying before, the most optimized version of the predicted data. And we do this through something called a loss function, which is much more straightforward and really just the difference between the observed mean values and the predicted mean values for the different data points. And there's some options in this, but they're pretty much all the same. Some, like there's the square mean, there's the least squares, there's a smoothed version of this. They're very similar to each other. And to give some diagrams to this, so again, this is not my Hubble diagram, this is me training my ANN. So if I'm thinking about the risk, which tells me how to choose the number of neurons, number of layers, you can see with these blue points, you can see very clearly, like sort of the fifth blue point is, in a sense, the best optimized part of this. And that's, you know, over here we're talking about number of neurons, 2 power n, where n goes from 7 to 14. So there's a lot of neurons. Just to speed up a bit for time purposes. So the loss function, on the other hand, seems to plateau. And this makes sense, because if I'm training my ANN, at some point it's going to keep giving me the same values when it's trained to an optimal point. It does look a bit more noisy, but in the end, it sort of plateaus. So that's what ANN would mean for us. Now, can we do the same thing? Yes, we can. We can get a Hubble diagram, H versus Z. So on the right here, we're showing this ANN reconstructed Hubble diagram for different layer combinations. In blue, we can see what's happening for one layer, which seems to be the best behaved, because the other ones show some oscillations that are not really there. And then on the left, we have what the different loss functions would give us in terms of the training procedure. And at the bottom, you can see the different estimates of H0. Now we're at the opposite end of the regime. And we can see this maybe better in this other slide over here, where I show a whisker plot of the values of H0 and their best optimized values. Now the uncertainties are really wide. So again, I want to emphasize these are techniques which are, in a sense, still works in progress, but which can start to inform, let's say, how to build models. They can help us get to that point, which is what we want to get at. Okay, so if now we have higher uncertainty, so if we try to rebuild our f of t, we get these weird plots. If we look at them, they look a little bit weird, right? But the thing to decompose them a little bit, they all have different data sets, all 3 plots have different data sets, and the ones on the right have priors, but they're pretty much telling us the same story. So what are they telling us? So in the dotted line, horizontal dotted line, we're seeing lambda CDM. The other lines are giving us, for the different data sets, the mean, how the mean curves away from that. And with the uncertainties, we can see how consistent we are with lambda CDM. So, sorry. So we're still very consistent with lambda CDM, but we can start to see the indications of possible veering away from that, or what that would look like for f of t. Now, this is not the be all and end all. So here we're looking only at f of t. What about in other regimes? So what does that mean? So before I was mentioning a lot Hondesky or scalar tensor. So let's look at that. Again, this is a method which is still being developed. So f of t may get better over time. Maybe different data sets will give us something stronger. Let's now, just as the last part of this reconstructed method, let's say portfolio, let's look at this identical slide on Hondesky theory. So in Hondesky theory, we're picking this G4, G4, this G2, G3, G4, G5, these functional forms. And I want to show you two very simple, relatively simple subclasses of the general Hondesky model. One being quintessence, which we may say is very simple, but this is a canonical scalar field that's minimally coupled, right? So at the top, I don't want to give a wall of equations, but it turned out to be this way. So at the top, on the left, we have quintessence and the functional forms of that. Then we have the background equations with the Klein-Gordon, and then finally the equation of state at the bottom. On the other side, on the right-hand side, we have so-called designer Hondesky, which if we do some algebra, some gymnastics, we can make this look at background identical to lambda CDM, and then we can hide the new physics in the perturbative sector. But I don't want to do that. I want to show all of this here. This depends on two functional forms, a K that depends on the kinetic term, you can see here, and also this G subscript X, so this G derivative X, and G depends only on X. So I care about those two functional forms, so the designer Hondesky. If we try to reconstruct our Hubbard diagram, it's the same story. So on the left, I'm looking at the Hubbard diagram. I'm looking at the Hubbard parameter versus redshift, and I get the same sort of picture. Why do I have different colors? Because I have different priors and for these slightly different data sets. But the point of this is that we agree very much with that black dotted line of lambda CDM, but with larger uncertainties. Now, if I had a functional form of the Hubbard diagram, the Hubbard function, finding its derivative would be a high school or below high school, very simple problem. However, we are trying to do model independent or reconstruction. So this becomes quite a non-trivial problem when we want to find a numerical derivative. And that's what we have on the right here. So in this work that I cite at the bottom, we're looking at how do we find that functional form. And the way that we find it is we take a numerical derivative of H prime, and then on top of that, we take a Monte Carlo routine to try and fix the uncertainties. Otherwise, the uncertainties will blow up and become totally unrealistic. We wouldn't have an answer at all. And I need this H prime because once you touch scalar tensor theories, you end up with an expression of H prime in your equations of motion. So just to show very quickly, if I look at the quintessence model, I'm able to reconstruct at the top left, I'm able to reconstruct the potential against redshift. So again, when we start to think, and this is very practical, was when we start to think about different potentials, if your potential doesn't have these characteristics, then okay, it may be correct, may not be correct. But if you're trying to get intuition or motivation for different functional forms, this is one way to do that. I also show the kinetic term and the equation of state, but I'm getting very close to the end of my time. So I want to try and move on to the other case where I have designer Hondesky. Here we see a lot more dynamics. So at the top, we're seeing that G subscript X, and we're seeing K, both against redshift. And again, here, okay, even with the larger uncertainties, we see a lot of evolution. This is very far away from a constant, right? And in fact, even in the equation of state, we're very far away from that dotted lambda CDM line. So where there's a lot of data, we agree. And when there's less data, we start to see some differences. at 2 to 3 sigma. So we start to get motivation for looking at non-trivial things. So that's, in a nutshell, really what I wanted to say about model building and these new ways of reconstructing fundamental physics models, but using data. What I really wanted to make the point about was that while we do reconstruction, and we really do reconstruction in the literature of trying to find different potentials for scalar tensor theories or functional forms like f of t, f of r, f of g, whatever. But we shouldn't be scared of using new methods. We should use the methods available to us, and in particular, the information that's contained in observational data. And this is one, I would say, promising method of doing that. And just in the last couple of minutes, I just want to mention Cosmology, because I don't think everyone is super aware about the action and also some of the things we're doing in this action. So just to show a couple of slides. So Cosmoverse is a network based in Europe, but with a global reach. So the in-person meetings are happening in Europe. Like we have these 2 nice meetings we had in Lisbon and this summer in Krakow. We also had a school in Corfu. And the point of this network is beyond that. We do more, I would say, online stuff, like seminars and other things. And what we really want to do is we want to connect this community, so the fundamental physics community, with both the things I was talking about today, data analysis and new methods of data analysis, but also with the observational community. Why? Because observation people may not really, we should be talking together to try and come up with solutions to these pressing and growing observational problems. Something practical to mention is that right now we're working on a white paper. Here's the URL of that, but send me an email and I can send this to you. Please be part of this. This white paper is going to be forefront fundamental physics, data analysis, observations, and we really want, it's a white paper, so we want everyone to be included. So please be part of this effort. And if you go on this link, you go into a view-only overleaf where you can add yourself as an author on a spreadsheet, and also you can contribute with comments, suggestions, that sort of stuff. And just to mention some in-person events that are coming up this year, there are more activities than just this white paper. So we'll go into our website, you can see them. But beyond that, we have some meetings coming up, one in Naples on observational cosmology, and then another one in June in Istanbul, which touches on all topics. So if you can make it to this, I think it would be very informative for everybody. Yeah, so that's like the Cosmoverse side of things. But to bring it all together, so I hope I've convinced you that, machine learning techniques have their place in probing new physics. We saw some examples with teleparallel gravity, with f of t, and teleparallel Hondesky, and also how these methods can be applied to classic Hondesky reconstruction or model building in classic Hondesky theory. Thanks for your attention. Hope this was informative. Cheers.
Thank you, Jackson, for the nice talk. Are there any questions in the audience?
I hope I didn't scare anybody with the machine learning techniques.
I guess Cheo has a
question. Actually, I have 2, but maybe I start with the naive one, or maybe. So when you mention the risky function as a function of the number of networks, neurons, could you explain why the risky function will increase with the number of neurons?
Okay. I think you mean here, right? That we sort of hit a minimum point and it starts.
Yeah.
So when we're designing neural networks, like when we're doing normal fitting, if you have, let's take normal fitting. If I'm doing MCMC, okay, if I have many parameters, what happens? The fits of those parameters become unstable because I have too many parameters for the underlying data. Similarly here, if I have too big of a network, the fits of these hyperparameters, even though still at that minimum point, we still have a huge number of neurons. But as I start to increase beyond the sort of legitimacy or robustness of the data, the fits on these hyperparameters start to become unstable, and basically the predictability of the hyperparameter in this case and its uncertainties becomes so much less robust. And if I look at, even if I just look at this functional form here, it starts to become all over the place. So H naught could start to vary between 90 and 50, which are totally unrealistic. And same thing for the 1 sigma uncertainties. So I'm not sure if that hits it, but basically it's about the stability of the neural network.
I see. And the second question, if no, I don't know, can I? Yeah, the second.
There's nobody else.
Yeah, the second question is that I'm still a little bit confused about when you mention model independent way, like eventually when you draw, for example, in FFT or Hodesky, you still need to assume some certain model and then use the equation of motion, the field equations of the theory to reconstruct those like FFT as a function of Z or Hodesky functions as a function of Z, right? So what do you exactly mean by model independent way?
You're right. So when I use the word model, what I mean is an explicit form of my Friedman equations. So here it's true that I have Friedman equations, or else I won't be able to say anything. However, these Friedman equations are a general class of something. That something is F or F of T. Now, afterwards, I show how this can give us the, scalar tensor theories. It's true, I need to make a decision somewhere. I need to say, okay, I want to, if I'm looking at, if I go to the very beginning, it would be a big dream, and we are trying to think how this can happen. But if I'm looking at this whole infinite space of all possible cosmological models, right now I can't imagine a case where we can probe this whole model space. But this lets us elevate from where we were a few years ago, where if I'm thinking about teleparallel theory, where I need, for instance, to choose F of T, I need to choose power law model. It lets us elevate a little bit. And instead of having a power law model, I can at least say, okay, I choose F of T, but all F of T's. And what do all F of T's give me? As a numerical reconstructed model. So that's where we're at the moment. Now you can say the uncertainties are too big, but numerically we can build pipelines that go from data and give us, as a result, a kind of model for these general classes of models. Or if I look at Hodesky, like I was showing you quintessence, I can go backwards and I can get almost a functional form of the potential. But yes, we do need to make a choice on which colored plots we're going to look at, or which colored box we're going to look at. I hope we can extend this more. And there's some interesting stuff happening with genetic algorithms in this direction. But it's way at its infancy. So we're very far away from looking at this whole model space right now.
I see. Thank you.
Cheers.
Okay, are there other questions? There's one in the chat. Thank you for the nice talk. Given the predicted age of Z, is it guaranteed that there are corresponding model parameters within a theory that can reproduce such curve?
So if I understand this correctly, and feel free to unmute, Amiba. So if I understand this correctly, we're asking, so if I choose, so just to jump way to the, sorry, if I jump way to the bottom again, so if I choose like here, so if I take the blue curve, for instance, if I choose a functional form that has the same sort of characteristics, like just by eye. Now, I don't know. It looks like there's sort of like an inflection point here, then a gradient going down. So if I choose a quadratic for my F of T, and I test it against the same data sets, I don't know in terms of statistical theory whether we are guaranteed, whether the word guaranteed is the right word, but I would expect in all cases that we would be able to find model parameters that would give us a good fit for this reconstructed for that particular data set. So yes, I would say so. But again, feel free to unmute. I hope that answers the question. Again, what we want is, we want to move away from ad hoc models. And when I say model, I mean an explicit functional form, to at least move towards a case where I have some intuition, some information. I mean, again, just to search the infinite model space of modified cosmology, we need extra information. That's either coming from symmetries, fundamental physics, that sort of stuff, or somehow stealing information from observations. And here we're taking that information from observations in a direct manner. So there's something to this, I hope. But I hope that you can see that there's something to this. Okay.
Are there other questions? Maybe I can ask one. I guess here you just basically use information from electromagnetic radiation, right?
Yes, so here we're using that cosmic chronometer, type 1a supernovae, and BAO data. But are you getting at the gravitational waves?
So what do you think would happen if you at some point can introduce gravitational wave to the mix and maybe also neutrinos from different sources?
So adding to the data sets that I'm showing, so here I'm showing sort of like the late time basic data sets. Adding more to this would be really super, super interesting, because while we have indications here, maybe if we can add more data to this, and adding more data means thinking very much about numerics we need for reconstruction, that side of things. But if that is possible, it may get us, in a sense, further away from lambda CDM, and maybe also decrease these shaded lines so that we can more explicitly write down a functional form. In terms of gravitational waves, direct measurements like this still have a lot of uncertainty, but it would be interesting to add that. Gamma ray bursts, we have some works going on at the moment on that. And even neutrino physics, there's a lot to be said there. So I totally agree. Would be very nice. We should talk more about that.
Thanks. I guess, Jay, you got another question?
Yes, it's actually not a question. I'm trying to think about the possibility of making this method more model independent. So let me first ask one question about is it true when you have the Hubble diagram, and then if you want to reconstruct those functions as deviation functions, whatever function as a function of z, the Freeman equation is only what you need, right? Is it true?
Yes. Well, if we're talking about data that has got to do with expansion. If I take perturbative data, I mean, there's a lot I didn't show here. So if I'm taking like data that has to do with large scale structure formation, then I would need to put in the perturbations, and this would be more convoluted. I hope.
So
okay. Yeah.
I see. Then can you, for example, we can try to parameterize the Fermat equation on top of the original GR Fermat equation, and maybe you can also consider cosmography approach when expanding the scale factor Hubble function, and you try to parameterize those deviation function from lambda CDM. And I think that if you do this, you don't even need to choose a class of models.
So you can do that. I mean, what I wanted to show here was how we can use this for model building in specific classes of models. But cosmography would be sort of I would say like the older version of this, because cosmography is trying to be model independent, but it obviously it assumes flat FLRW, and then we try to fit the parameters beyond that. The problem of cosmography is that there's no way to escape that the cosmographic parameters are highly degenerate with each other.
Oh yeah, that's right.
Whereas in this case, we don't suffer from that degeneracy. But yes, cosmography could be another way. In a sense, this is like PPN, right?
Yes, exactly.
If we parameterize our PPF, if we parameterize our deviations from lambda CDM, then we can apply those and build models. I wanted to show directly how we can use this to build models, how to get into of functional forms. But you're totally right. It would
I
be
see.
interesting. Again, I don't know why this hasn't been taken up more by the community to build models. I think every day on the archive, I see different papers on building different models of cosmology or in general astrophysics using a very abstractized version of the data I'm showing here. Why not just use the data in the first place?
I agree. Yeah, so it's kind of a trade-off between like the amount of degeneracy and also the number of the additional parameter, arbitrary parameters.
Yeah, no, I agree. So we don't get nothing for nothing. However, you know, there's so much work going into machine learning techniques. I think we shouldn't ignore the sort of portfolio of techniques that are being developed here. And here I just spoke about two. I just mentioned genetic algorithms. That's also very powerful in model selection.
I see. Thank you very much.
Excellent.
Okay, are there other questions? If not, I would suggest to end the official part here so that people who have questions and don't want to do it while it's recorded have the option to do so.